In this video, we're going to talk about the topic of data representation, which is covered in Chapter 3 of your textbook. We're going to talk about why data needs to be represented in the first place, exactly what we mean by data representation, which basically gets us into discussion of data types, things like integers and real and what have you, and different formats for representing those types within a computer system or within a CPU, and we're going to compare and contrast those, talk about their advantages and disadvantages, and when you might choose one versus the other of those alternatives. Okay, so what are we talking about when we're talking about data representation? Well, first thing to realize is that data representation and data processing go hand in hand. There's really no way to separate the two. And the basic issue here is that any sort of processor, be it an Intel CPU or an AMD CPU, or be it a human brain or anything else we can think of, it has a certain internal implementation, and the way we represent data has to be compatible with that internal representation. And if the data that we want that processor to process doesn't quote-unquote start out in that compatible representation, well, then we have to go through a process or a series of processes by which we convert it into a format that is suitable for that processor to manipulate, or a very general word here would be understand. Okay, so let's expand a bit on this concept of understanding. What exactly do we have to do? Well, first off, the processor, well, has to, as we said, it has to deal with the data in its own internal format, okay? And assuming that processor is responding to its environment or accepting data from the outside world, we have to first recognize what that data is. We have to see it and be able to say, that's something I want to process. And then we have to go through a conversion process to convert it into whatever format internally is usable by the machine, okay? We, of course, may also need to store and retrieve data from various storage locations, things like registers inside the CPU, things like primary and secondary storage devices, things like the shorter long-term portions of your brain. Okay, we have to be able to transport that data representation from storage devices to processing devices and back and vice versa, or amongst internal processing components. So, for example, say from the control unit to the arithmetic logic unit, or vice versa. Okay, and of course we have to be able to manipulate that data to do whatever it is we want to do with it. We need to add it, subtract it, compare it, whatever. So let's make an analogy to the human brain. Okay, and there's two reasons for doing this. One is most students have at least talked about brain physiology in some biology class somewhere along the way, be it college or high school. The other is, well, we'll come back to what the other is. So let's think of the brain as a processor. Let's think of the brain as the equivalent of an Intel CPU. How does the brain work internally? How does it do its processing? Okay, what's its basic way of operating? Okay, well, I'm going to jump down to the fourth bullet here. Okay, our brain is a series of interconnected neurons. Okay, each of those neurons is basically an electrical chemical processor. Okay, it's not quite a switch. The analogy to a switch or a transistor is certainly not perfect, although there are some similarities. Okay, and so the basic way we represent data and transport it and use it is electricity. Okay, we use some chemical reactions to kind of, amplify or route the electricity here and there, and of course the internal neuron is itself a biochemically based device, but it's really electricity that transports the data from one place to another. Okay, which is why we go so gaga when we get electrical shock, because it kind of, overloads the whole system. Okay, so we know that the brain is going to operate on data represented as electrical impulses. Okay, how do we get the data we need to process converted into electrical impulses? Okay, because most of the data our brain processes does not come directly as electricity. It's not like we, pull out some sensory device out of our ear and plug it into a wall, plug it into a power outlet, and comes the data. It might be nice. I've often thought it would be nice to study if, I had a little USB port in my neck and I could just wire myself into the internet and download and assimilate information while I slept. Doesn't quite work that way. What we've got, imperfect as it is we have 5 senses. Okay, we have touch, we have taste, we have smell, we have sound, and we have vision, or hearing and vision. Okay, and they allow us to take quote-unquote data from the outside world and convert it into the electrical impulses that our brain can process. So, for example, let's take vision. Okay, there are receptors on the back of our retina. Light comes through the lens. It's focused on the back of the retina. The retina recognizes both intensity and color. It converts all that into a series of electrical signals, which are passed through the optic nerve, and the optic nerve travels to the back of our head, to our visual processing center, which is basically the back portion of our brain. And that's where things like, scene recognition and face recognition and, anything to do with visual processing. How fast is the ball coming, and do I need to duck, and am I going to be able to swing the bat in time to hit it? Those are all the kind of things that we do processing-wise with vision. Okay, so we have very specific organs, okay, that are designed to take external stimuli of some sort and turn them into electrical impulses that our brain can process. That's the suitable internal format. Okay. What about storage? Well, we've got dedicated regions in the brain for short-term storage, read seconds or minutes, and long-term storage, read, many minutes to many years. Okay. We move the data back and forth amongst the storage and the processing functions, or amongst various parts of the processing functions. Once again, it's electrical signals transmitted neuron to neuron. Okay. The processing results, okay, can be stored internally. Okay, so think I'm just sitting there thinking about a problem, and my only quote-unquote result of that thinking or processing is to come to a conclusion and store the conclusion in my long-term memory. Or we can direct physical actions. Okay, so we can move our arms, we can wave our hands, we can speak, we can stand up and, jump out of the way of approaching danger or whatever. Once again, all based on electricity. So the point in doing the brain analogy, as I said, is most people have some understanding of brains, but the other is to realize that when we talk about data representation and we talk about processing, it really doesn't matter whether we're talking about computers as we know them now, computers as we may know them at some point in the future, or human processors. Okay, the basic functions, these basic things we need to do to grab data, turn it into something that the processor can understand, crank it through the processing mechanism, shuffle it back and forth to storage, and eventually produce some action or some new stored knowledge from it. Those are the same. Okay. All right, so now let's talk about the modern world of modern computers. Okay, so you go out and you buy that new laptop, and it's got a Intel Core i7, God knows what model number. Okay, what the hell's actually inside that thing? Well, when you get down to the basics, okay, there's really only 2 things inside that CPU. Okay, there are a couple billion electrical switches, and there's a bunch of wiring to connect those switches. Sounds pretty simple, but of course when anything's measured in the billions, it's anything but simple. Okay. Clearly we need to do things more complicated than just on-off, which is what a switch does. Okay, and we do that by taking groups of switches and wiring them together to produce complex circuits. So for example, an add circuit, a compare circuit, a less than or greater than circuit, a division circuit, so on and so forth. Okay. Each of these switches is what's called a two-state device. Okay, so when you think of a switch, literally just think of a switch like a light switch on the wall. There's only 2 possible states for that switch. It's either open or it's closed. Okay, there's no halfway, there's no quarter way, there's no tenth of the way. Okay, it's not 1.2675% open. It's either open or it's not. Okay, electricity is either passing through it or it isn't, and those are the 2 states. Open or closed, on or off. Electricity moving through or not moving through. Okay. Well, if we wanted, we could represent each of those positions, off, on, open, closed, with a binary digit. Okay. A binary digit, one number, has 2 possible values, 0 or 1. Okay. And we could use the 0 to represent open and the 1 to represent closed, or vice versa, and it doesn't really much matter which we do as long as we're consistent about it. Okay. So we know that the insides of the processor are these two-state devices, open or closed, which basically means electricity is moving or not, and we can represent open or closed as a binary 0 or 1, and that's basically our tie between the data representation and the modern processor. Okay. The data representation at its most elemental level is a set of binary digits, each of which can only have the values 0 or 1. Okay. If the data that we want that Intel processor to process is already represented as a set of binary digits at an with electricity at an appropriate voltage and amperage, then no problem. So in other words, if we're reading from RAM, okay, RAM stores data in the same way, and we simply move the electrical signals from one device to the other. If, on the other hand, the data we want to process has to come from somewhere else, say a visual scene or a digital camera or whatever, now we've got a fair amount of work to do in capturing the light, capturing the light and generating a set of binary digits that represent the content of the light and passing those on to the Intel processor so that it can do whatever it's going to do with that visual data. Okay, so there is a data conversion process when we're dealing with anything that is not quote-unquote naturally a binary digit or a set of binary digits. Now, let's briefly digress and talk about the pros and cons of this fact that a modern computer basically does nothing but process binary digits. Okay, it only processes binary digits, but as we all know, it does it extremely quickly and extremely accurately. So if the data that we want to process is either binary digits to begin with or is sort of quote-unquote naturally compatible or convertible to binary digits, then that modern CPU is very well suited to processing that kind of data. So for example, let's just pick on accounting. I mean, what does accounting do? It deals in numbers. Okay, it adds them, subtracts them, multiplies them, divides them, sums them up by category, and makes financial statements out of them, so on and so forth. Okay, the numbers themselves are naturally convertible to binary digits. Even if they're not represented in binary, it's a relatively straightforward process, at least to a computer, to convert them into binary. Okay, so since the data we're processing is inherently numeric, okay, the modern processor is very well suited to representing and manipulating that data. Now let's flip around to the other side. Let's say, for example, I want to program a computer to accept its input from a digital camera that's mounted over the various entranceways to the Super Bowl. And I want to do that because I want to scan faces passing under that camera and basically try to take each of those faces and see, is this a known terrorist? So go search my database of terrorist faces and see if I've got a match. Okay. That's a whole different ball of wax in terms of its suitability for processing by this Intel Core i7 whatever processor. Why? Because light is not inherently binary. Okay, light is analog. Okay, light can vary intensity from none to a very high level and a whole range of things in between. Okay, light also has color, so it's not just a matter of intensity; it's also a matter of color. And of course, when we're talking about recognizing a face, we have to deal with a lot of different points of light. We've got to deal with a whole visual scene. And of course, we've got to deal with things like, lighting and shading and which way is the face facing and is it moving or is it standing still and, is the person wearing a hat or not wearing a hat or sunglasses or whatever, so on and so forth. But the bottom line is the visual data, particularly a moving image, is not something that we immediately think of as a set of binary digits. Now, of course, we do have visual cameras and visual camcorders, so obviously somebody's figured out mechanisms by which we take that light, either still or motion, and convert it into a set of binary digits. But it's a complicated process. I mean, flip phones fairly, or a flip video recorder is fairly cheap, but there's a lot of technology inside there, and its basic purpose is to do nothing but take incoming light and convert it to a stream of binary digits. Okay, and it's a complicated process, even though we've packaged it into a device that we can sell for $100 or less. Okay. Now, that basic conversion process, well, it's not basic, but that conversion process is A, complicated, B, slower, well, slow because it's complicated, and C, it's also subject to error. Okay. All three of those things mean that once we've done the conversion to binary data and we digits and feed it to the processor, we can't expect perfection out of that processor because the data coming in may or may not have been perfect, but clearly it's not perfect after it goes through the conversion process. And the more complicated the conversion process, the more possibilities there are for error or misrepresentation, and the less reliable becomes the processor with respect to any sort of manipulation of that data. It's not that it's going to drop calculations, it's just that the numbers that it's calculating may or may not be an accurate representation of the data that of the data that in fact we are talking about, the visual data, not the numeric representation. Contrast that with how our brains process pictures. Okay, we have no trouble dealing with color. We have no trouble dealing with moving versus still images. We have no trouble dealing with wide variations in light. Okay, why don't we have any trouble with that? Because our brain processing circuitry is optimized for it. Why is it optimized for it? Well, thank evolution. Our mammalian ancestors right up through us, have basically for 100 million years or so been playing the game of eat or be eaten. And a big part of that game is scanning the visual world and seeing, is there a danger out there that's about to eat me? Oh yeah, that predator off in the distance. Are they close enough to run over here before I can get to my little burrow in the hole and get away from them? So clearly, those of us who developed the visual abilities to answer those kind of questions successfully, got to hang around and pass on our genes, and any genetic mutations or adaptations that improve that process, well, they got passed along too. So call it the miracle of evolution. But the bottom line is we have a brain that's optimized for that purpose because it was very much to our advantage for 100 million years to be optimized to that purpose. Okay. Computer processors, on the other hand, are much more limited in that respect. So, we've got a trade-off here. If we want to crunch numbers or numeric data or something easily converted to numbers, and we want to do it accurately and fast, well, clearly we don't want a human doing that in their head or with a paper and pencil. We want a computer doing that. On the other hand, very complicated things like visual analysis, while we'd like to get computers to do them, it's tough to get a computer to do it with the same accuracy as a human can. So which do we do? Do we come up with a computer program that's looking at all those cameras of the people walking through the Super Bowls, or do we hire some, army of, people, train them with the faces of known terrorists, and have them watch the folks as they go by, seeing that they recognize somebody? Okay, so we've talked about why we need binary numbers, so sort of take that as a given now. So what the hell is a binary number? Well, we already know binary digit, at least, has is a digit that has either one of two values, either 0 or 1. So a binary number is either one of those bits, or it's a series of those bits that together mean something, a sequence of those. Okay. And the advantages are obvious, as we've already said. They match very well the internal processing circuitry, the two-state processing, and we like two-state because it's cheap and easy, at least for us at the moment. We also like it because it's easy to transport reliably, and that's something we'll get to in Chapter 8. But final beating to death at this point, both of these advantages are based on existing technology. Okay, roll the clock forward 10 or 20 years, and maybe that technology takes some unexpected turns. Maybe a fundamentally new technology comes along, and we figure out how to apply it to computing, and it works some other way. It doesn't need binary numbers. It does something else. Okay, so the bottom line is the future technology changes may make the approaches to data representation completely different. Okay. Will that happen in your lifetime? Maybe. Will that happen in my lifetime? Probably not, but we'll see. Okay, another advantage, another handy correspondence, okay, with binary data is that binary data maps directly to something called Boolean logic. George Boole was an English mathematician, and he was basically the first person to write down the formal body of knowledge that we now know as Boolean logic. And it's a relatively simple body of logic, but of course, the first person to write it down, they get credit for it. And, So that deals with things like, conditions, less than, greater than, anything that can be evaluated to true or false, not any values in between. And Boolean logic describes how these things kind of combine together. So for example, if condition A is true and condition B is true, does that make condition C true? Or is it A or B? And what if both conditions are false, or both conditions are true, or one is false and one is true? If you've done any programming, you may have worked with something called truth tables. These are a direct representation that comes right out of Boolean logic. Okay. Why do we like Boolean logic? We like Boolean logic because it's the basis upon which most computers do anything that we would remotely consider intelligent in manipulation of data. So for example, this if statement down at the bottom here, just about any bank program is going to have this. So you walk up to the ATM, you ask to withdraw $1,000, but there's only $500 in your bank account, so you fail this condition. What happens then? Well, electric shock comes through, eats your card, and it automatically calls the police to come pick you up for being a vagrant or what have you. Okay. But the bottom line is Boolean logic is what drives this process. Boolean logic, because it deals with true or false, maps very well to binary numbers. 0 true, 1 false, or vice versa. Once again, doesn't matter. Pick a convention and stick with it. Okay, and that corresponds directly back to the binary digits.